Walaikum Assalam.
Today we will discuss continuous random variables. Variables such as height, weight or temperature are continuous. And how we express it. Suppose the variable x of interest is the depth of a lake at a randomly chosen point on the surface. Let m be the maximum depth in meters so that any number in the interval 0 to m is a possible value of x. So the range of x will be in the form of an interval or the union of some disjoint intervals. We will discuss some probability distributions for continuous random variables. First one is the normal probability distribution. Normal probability distribution having its curve normal and symmetrical, as we have discussed in our first chapter. Let me find the diagram. Okay. For a normal probability distribution, the variable will have a range from -infinity to +infinity with the probability density function like this. The diagram for this normal probability distribution is let me find again. Normal curve we have of this form. Just a minute. I need to show you the diagram. picture from desktop. Why I am not able to save the picture? This one is a normal curve. I need to shift it in the text. So this type of the curve is called a normal curve. Why I need to show this diagram? As this diagram is normal and symmetrical, that's why particularly the mean value will
एक्सक्यूज मी सर, सर आपकी आवाज़ नहीं आ रही, माइक ऑफ है आपका आई थिंक।
I'm sorry. So we were talking about the normal curve. Remember one thing, that in this normal curve, mean is in the center, and we find probability in the form of uh, for any sub interval of the range. Let's say from A to B, we need to find out the probability. For this purpose, we will integrate the density function from A to B. This will be the area under the curve for this particular range. And how the area may be, uh, we can have in different problems. We have areas of the form, let's say, of this form. Either we need to find the probability for this region, that's mean the probability for x less than a. When we need the probability for x greater than b, this may be this b point may be here or here, anywhere on this x-axis. But we find the probability for all the points which are greater than this fixed point b. So let's say this point B is here in right half. So the meaning of this probability for x greater than B is the shaded part as shown in this figure. Sometimes this A and B gives an area in the form of a strip, and sometimes this strip is in the left half, and sometimes this area under the curve is of this form when one point is in left half and other point is in right half. And sometimes the probability for x less than b is of this form in a problem. So how to deal with? Either we integrate or we use the table to approximate the area under the curve. Integration is time consuming and a little difficult. So we prefer a table to approximate these areas. So in different problems, we have different mean and variance. So for each mean and variance, we must have a different table. So this is not possible because in a particular, for a particular random variable, the mean and variance is fixed. So we must have a table for this particular distribution with mean and variance. So this is not possible. So that's why first we standardize our variable. And we have a table for this standard normal variable. How we standardize it? We put z is equal to x minus mu over sigma. This z variable is standard normal with mean 0 and variance 1. Because whatever is the mean and variance for a variable x, when we standardize it, when we convert in terms of z, its mean becomes 0 and variance 1. That's why this is called standard normal variable. Now this is a convenience for us because we have a uniform criteria. Whatever is the problem, when we convert in terms of z, we have mean 0 and variance 1. And remember, in our curve, in our normal curve, mean is in the center. Okay, and next step is the use of the table. We have a particular capacity of the table. The table measures the area from 0 to a fixed point in the right half. We can measure the area shown with the pink shade from center to a particular point in the right half. So what should we do with different problems? Look at the situation. Now, as all these diagrams are normal and symmetrical, that's why here we have a line of symmetry. This dotted line is a line of symmetry in all the cases. So when we need to calculate this area, we will imagine a mirror reflection in the right half. When we have a strip in the left half, we will just imagine a mirror reflection in the right half, because table works only in right half. So what will be this change? When we reflect this area in right half, this point which is negative, all the points are negative when we change our variable in terms of z. What is the reason? Because we have 0 in the center, so all the points which are on the left hand side of the mean are negative, and all the points which are on the right hand side of this mean, they are positive. Remember, this thing is only for the variable z. When we convert our variable in terms of z, then the point will be negative when it is in the left half, and point will be positive when it is in the right half. Okay, when we imagine a mirror reflection, or how can we imagine a mirror reflection of this shaded part in the right half? Just we change this sign, negative to positive, because its mirror reflection is with plus a in the right half. So in this way we will calculate this area. Okay, next step is, table has a fixed capacity. It measures area from center to a fixed point. If we have this problem, first of all, we convert our point in terms of z, and then we will use this point in the table. Table will provide us the area from center to this point. This will be the area. This will be the area. This is called the tabulated area. But we need this area, this green shaded area, as the total area under the curve is 1, because this curve is or a probability function, and total probability is 1. That's mean, in other words, the total area is 1. That's why half of the area is in right half and half of the area is in the left half. So if this shaded part is our tabulated area and total half is 0.5, so subtract this tabulated area from 0.5, we will get this area. We will get this area. Similarly, when we need this strip, consider these points with positive sign. One thing, if the required area is in the left half. Okay, our this point will provide us the area from center to this point. And this will be the area. This will be the area from center to this point. Okay, what about the other point? Other point, for other point, the corresponding area is this one, from center to this point. So we have two areas for these 2 points. Subtract the smaller area from the larger one. We will get this strip. Okay. What about this area? We need this area. So what will we do? First of all, we will convert these points in terms of z, and we will use these z points in table. Table will provide us the areas from center to this point and from center to this point. As we need this total area, so we will add these tabulated area to find our required probability. And what about this one? Single point we have, convert it in terms of z. Table will provide us the area from center to this point. From center to this point. But we need the complete green shaded area. So we will add this half to the tabulated area. So what is our required area? 0.5 plus tabulated area. This will be the required probability. This will be the required area. Now let me check some problems. For example, our variable is normally distributed with mean 10 and standard deviation 2.1. Sometimes we are not given a statement. We just have a symbolic expression like this. If I express this above statement in terms of symbols, it will be like this. Okay. we have this situation. According to our problem, our variable is normally distributed with mean, 10 and variance. In this sentence, we are given standard deviation, but in symbols, wherever we have this symbolic notation, the second component is always the variance. So 2.1 square is 2.1 4.41. So here we have variance 4.41. So, sometimes we are given the information in the form of a statement. Sometimes symbolically we are given this statement. Remember, the first component is showing the mean and the second component is always the variance. Okay, but we need to find out the probability in first part. The probability for x greater than 11, and in second part the probability from 7.6 to 12.2. So first of all, we must draw the curve. This curve is for our first part. We need this shaded area. In second part, we need the probability from 7.6 to 12.2. Why we have mentioned these points, one on each side? 7.6 obviously is in the left half. First of all, show the mean value. Mean value is 10. So 7.6 will be on the left hand side of this mean value. The other point is 12.2. So 12.2 definitely will be on the right hand side of this mean value. That's why we have figure of this form. Okay. What is the procedure? We convert these points in terms of z using this z formula. The corresponding point for x equal to 11 is 0.48, and the corresponding points for 7.6 is minus 1.14, and the corresponding point for 12.2 is 1.05. Now we use the table. For this point, for z is equal to 0.48, table will provide this area from center to this point. That's why we will subtract this tabulated area from 0.5. This is the tabulated area. 0.5 minus tabulated area, we will get the required probability. In second part, the probability for first part is 0.3729, and the area for second point is 0.3531. Look at the diagram. These are the two tabulated areas, this one and this one. That's why we will add both the tabulated areas. Now the thing is how to use the table. This is our table. Carefully understand the use of this table. We have a converted point z equal to 0.48. How to find the area corresponding to this point? Up to first decimal, separate the point. Up to first decimal we have 0.4, and second decimal is 0.08. If we join them, if we add them, again we will get 0.48. I mean to say that up to first decimal we will trace out in first column, and second decimal will be traced out in first row. Now 0.4 in first column and 0.8 in first row. 0.4 in first column, first decimal, first column, and second decimal in first row. Join them, we will get this area. This is the area corresponding to the point 0.48. And also you must remember, where is this area located in the diagram? This area is always from center to this point Z. That's mean this area from center to this point. This is our tabulated area. That's why we subtract tabulated area from 0.5 to get the required probability. Also, check the other points. The other point is 1.14. So up to first decimal, 1.1 in first column, 1.1 in first column, and up to second decimal. Second decimal is 0.04. In this way, we will divide this point. We will split this point, 1.1 plus 0.04. For the verification, add them, we will get the same point, 1.14. So 1.1 will be in first column and 0.04 in first row. 1.1 against 0.04, this will be the area. Again, this area is from center to that point. From center to the point 1.14. Our third point is 1.05. It is 1.05. So up to first decimal 1.0, 1.0 in first column. This is our one point zero. So below 0.005, second decimal is 0.05. So below 0.05 against 1.0, this will be the area corresponding to 1.05. Again, remember, this area is from center to this point. Then come to your requirement. Sometimes we add both the tabulated area. Look at the diagram. Look at the diagram once again. In first case, we subtract tabulated area from 0.5. In this case also, we subtract tabulated area from 0.5. In this case, we subtract smaller area from the larger one. In this case also, we subtract smaller area from larger one. In this case, we add both the tabulated area, but in this case, we add 0.5, complete half to this tabulated area. It depends upon the problem. It depends upon your requirement. Now check some other problems. For example, we have this situation. Lifetime of an automatic dishwasher is normally distributed. So quickly draw that diagram and point out the mean value in the center. Okay, if the dishwasher is guaranteed for 12 months, what is the fraction of the sale will require replacement? And that means the claim will be accepted. What fraction of the sale? What fraction of the sale will require replacement? That means we will accept the claim. This guaranteed period is 12 months, but mean and variance are given in years. So first of all, convert all the information in the same units. So this guaranteed period is now 1 year. Okay. What is required? A claim will be accepted if a device is not meeting its warranty period. If it is not crossing its warranty period, the claim will not be accepted. As it is crossing, uh, the claim will be accepted. But as it is crossing the warranty period, the claim will not be accepted. So what you have to do, let we have this diagram. In the center, we have 3.5 as the mean value. And as 3.5 here we have, so 1 is definitely on the left hand side. 1 is here. So this proportion will need replacement because this proportion is not crossing the limit of warranty period. So this shaded part is required. So first of all, we will convert this point in terms of z and find the corresponding area. This area will be from center to this point, but we need this one. So subtract this tabulated area from 0.5 from this total half. As you subtract this tabulated area from 0.5, you will get your required probability. Similarly, try to solve this problem. Let me read this statement. X denotes the height of soldiers. Okay, mean is 68.22, variance is 10.8. How many soldiers in a regiment of 1000 would you expect to be over 6 feet? Again, first of all, change the units. As mean and variance are in inches, so convert 6 feet in inches. We have 72 inches. So what is the probability we need? We need the probability for greater than this limit. We need over 6 feet, means greater than this figure, we need the probability. Again, let we have mean in the center, which is 68.22. So definitely 72 will be on the right hand side. But we need the probability more than 72. More than 72 is this area, this region. This region we need in this case. So convert 72, this point, 72, in terms of z and find the corresponding tabulated area. This will be the area from center to this point. But we need this one. So subtract tabulated area from 0.5, you will get this region. And multiply, this region is actually the probability. Probability means the proportion, fraction. So multiply this proportion with 1000. You will get the exact figure. Similarly, try the other points also. If you face some problem, you can discuss with me. But next distribution is one more thing I need to discuss, that is normal approximation to binomial. When we think that problem just like binomial distribution, due to large calculation, we approximate this problem with the help of normal distribution. Okay. A fair coin is tossed 20 times. Find the probability that number of heads occurring between 10 and 14 inclusive. You will include 10 and 14 inclusive by using normal approximation to binomial. That's if we calculate this problem with the help of binomial probability distribution, calculate this probability for x equal to 10 plus probability for x equal to 11 plus probability for x equal to 12 plus probability for x equal to 13 plus probability for x equal to 14, because endpoints are inclusive. So we will calculate this probability first for x equal to 12. We have the coefficient 20, C 10 and P power 10, further Q power other than these 10. So this is the probability for x equal to 10. Now just for a moment, the probability for x equal to 11 will be like this. 20C 11 will be the coefficient, P power 11 definitely, and rest of the figure will be for Q power. The others are the failure, which are 9. Other than 11, we have 9. And so on, plus so on. This will be the procedure if we are using binomial probability distribution. But if we approximate this problem with the help of normal distribution, so we need in normal probability distribution, we need the mean value. So use the mean value of the binomial, which is equal to NP. This is our mean value. Okay, NP is equal to 10, and sigma, value of sigma is 2.24. Now we have the mean and standard deviation for our variable. So one more thing, as 10 and 14 are inclusive, so to include these extreme ends, whereas in normal distribution, In all these possible cases, whether we have an equality less than or equal to or strictly less than, whether we have greater or equal to or strictly greater than, a less than or equal to x, x less than or equal to b, or strictly less than we have the same probability. But as in this case we are approximating our problem, our binomial problem, with the help of normal distribution, so intentionally we have to include these extreme ends. For this purpose, we have to expand this range by 0.5. Either 0.5, we also have some other rule to expand this range. If we go 0.5 on the left of 10, the point will be, we will stop at 9.5. If we move from 14 to rightward of this point, with the step of 0.5, we will be at 14.5. So we will use 9.5 and 14.5 for the calculation of the probability. So first of all, convert these points in terms of z. In terms of z, we have 2 points. One negative means that is on the left hand side, and this positive point means that is on the right hand side. So we need this probability. Again, we must draw the diagram. The diagram will be of this form, So as we have converted our points in terms of z, so for this point we will get this area, and for this point we will get this area, and the probability from this point to this point is needed. That's why we will add the tabulated areas. We are adding tabulated area, getting the required answer. So we have this normal approximation necessarily to apply when we have such situation. For example, a pair of dice is rolled 180 times. Use the normal approximation. Otherwise, it is too much difficult to expand a binomial expansion with power 180. That's why we approximate such problem. Otherwise, we have to add up the terms from 33 to 41. So it is time consuming and difficult. It will include certain errors. So that's why it is better to approximate with normal distribution. So we have some problems, solved problems for this purpose. So remember, this is the technique. We have to expand our range. Our required range is A to B, as this range showing that the extreme ends are inclusive. So we must expand the extreme ends with 0.5 by subtracting 0.5 from left hand point and adding 0.5 to right hand point. And next is a uniform distribution. That is very simple. Don't think about its probability function. Just look at the problem. We are given a probability function. This is our probability function, and it is a constant. F of x is 0.05 for the whole range from 0. This remains constant. That's why this distribution is uniform distribution. Okay, what is to calculate? We need to calculate the probability for less than 10. This is needed. So we will integrate our density function from 0 to 10. From initial, less than 10 means we will start from the initial point up to 10. We will integrate our density function from 0 to 10. This will be our required answer. Let's say if we need the probability from 5 to 20, so we will integrate our function from 5 to 20. So that is more simple. But particularly this problem, for example, let x be the thickness of washer and assumes a density function f of x is equal to kx, where for this range. This is our probability density function. That's why this is a probability function for this range. Okay, first of all, find k. Integrate this function. Integrate this function like this. First part, we integrate our probability density function we integrate our probability function f of x and equating to 1. What happens on the left hand side? We have integral kx dx equal to 1. And what happens next? We have k here by 2 is equal to 1. And with the range, we have to integrate this function within the given range. Okay, the range in this case, in our problem, the range is from 1.9 to 1.9 to 2.1. 2.1. Okay. So as we integrate this function, apply the limit. Apply the limit from 1.9 to 1.9 to 2.1. Solve this equation and getting the value of k. This will be the procedure. Now, as you get the value of k, now you are able to find the probability for any subinterval of this range. For example, what is the probability that the washer will have thickness between 1.95 to 2.05? So we will integrate now our density function after putting the value of K. We will integrate from 1.95 to 2.05. This will be the answer of second part. So that is the end of this chapter. We will discuss regression and correlation next week, inshallah. Today I will send this text on the WhatsApp group. So in this way, you will have two questions from discrete probability distribution, one from continuous and one from regression and correlation for final exam. I will also send the detail after completing this course. Okay, dear, Allah Hafiz.